Hi, this is Sleeper. Welcome back to my channel. We are continuing with the Bug Bounty job role path on Hack the Box Academy with file inclusion. If you need access to Hack the Box Academy, I definitely recommend the Silver Annual Plan, as it gives you access to all of the job role paths, all modules up to and including Tier 2, with an exam voucher, good for 2 exam attempts. You can check that out with the link below. So let's go ahead and continue with remote file inclusion, RFI. So far in this module, we have been mainly focusing on local file inclusion, LFI. However, in some cases, we may also be able to include remote files, remote file inclusion, RFI, if the vulnerable function allows the inclusion of remote URLs. This allows two main benefits. One, enumerating local-only ports in web applications, for example SSRF, and two, gaining remote code execution by including a malicious script that we host. In this section, we will cover how to gain remote code execution through RFI vulnerabilities. The server-side attacks module covers various SSRF techniques, which may also be used with RFI vulnerabilities. Local versus remote file inclusion. When a vulnerable function allows us to include remote files, we may be able to host a malicious script and then include it in the vulnerable page to execute malicious functions and gain remote code execution. If we refer to the table on the first section, we see that the following are some of the functions that, if vulnerable, would allow RFI. As we can see, almost any RFI is also an LFI vulnerability, as any function that allows including remote URLs usually also allows including local ones. However, an LFI may not necessarily be an RFI. This is primarily because of three reasons. One, the vulnerable function may not allow including remote URLs. Two, you may only control a portion of the file name and not the entire protocol wrapper, for example, HTTP, FTP, HTTPS. And three, the configuration may prevent RFI altogether, as most modern web servers disable including remote files by default. Furthermore, as we may note in the above table, some functions do allow including remote URLs, but do not allow code execution. In this case, we would still be able to exploit the vulnerability to enumerate local ports and web applications through SSRF. Verify RFI. In most languages, including remote URLs, is considered as a dangerous practice as it may allow for such vulnerabilities. This is why remote URL inclusion is usually disabled by default. For example, any remote URL inclusion in PHP would require the Allow URL Include setting to be enabled. We can check whether this setting is enabled through LFI, as we did in the previous section. However, this may not always be reliable, as even if this setting is enabled, the vulnerable function may not allow remote URL inclusion to begin with. So, a more reliable way to determine whether an LFI vulnerability is also vulnerable to RFI is to try and include a URL and see if we can get its content. At first, we should always start by trying to include a local URL to ensure our attempt does not get blocked by a firewall or other security measures. So let's use HTTP 127.0.0.1 at port 80 index.php as our input string and see if it gets included. As we can see, the index.php page got included in the vulnerable section, for example, history description. So the page is indeed vulnerable to RFI, as we are able to include URLs. Furthermore, the index.php page did not get included as source code text, but got executed and rendered as PHP. So the vulnerable function also allows PHP execution, which may allow us to execute code if we include a malicious PHP script that we host on our machine. We also see that we were able to specify port 80 and get the web application on that port. If the backend server hosted any other local web applications, for example port 8080, then we may be able to access them through the RFI vulnerability by applying SSRF techniques on it. Note, it may not be ideal to include the vulnerable page itself, for example index.php, as this may cause a recursive inclusion loop and cause a DOS, denial of service, to the backend server. Remote code execution with RFI. The first step in getting remote code execution is creating a malicious script in the language of the web application, PHP in this case. We can use a custom web shell we download from the internet, use a reverse shell script, or write our own basic web shell as we did in the previous section, which is what we'll do in this case. Now all we need to do is host this script and include it through the RFI vulnerability. It is a good idea to listen on a common HTTP port like 80 or 443, as these ports may be whitelisted in case the vulnerable web application has a firewall preventing outgoing connections. Furthermore, we may host the script through an FTP service or an SMB service, as we'll see next. HTTP. Now we can start a server on our machine with a basic Python server with the following command as follows: sudo python3-m http.server and our listening port. Now we can include our local shell through RFI like we did earlier, but using our IP and our listening port. We'll also specify the command to be executed with and cmd equals ID. As we can see, we did get a connection on our Python server, and the remote shell was included, and we executed the specified command. Tip: we can examine the connection on our machine to ensure the request is being sent as we specified it. For example, if we saw an extra extension .php was appended to the request, then we can admit it from our payload. FTP. As mentioned earlier, we may also host our script through the FTP protocol. We can start a basic FTP server with Python's pyftpdlib as follows. This may also be useful in case HTTP ports are blocked by a firewall, or the HTTP ://string gets blocked by a web application firewall. To include our script, we can repeat what we did earlier, but use the FTP scheme in the URL as follows. As we can see, this worked very similarly to our HTTP attack, and the command was executed. By default, PHP tries to authenticate as an anonymous user. If the server requires validation, then the credentials can be specified in the URL as follows. SMB. If the vulnerable web application is hosted on a Windows server, which we can tell from the server version and the HTTP response headers, then we do not need the allow URL include setting to be enabled for RFI exploitation, as we can utilize the SMB protocol for the remote file inclusion. This is because Windows treats files on remote SMB servers as normal files, which can be referenced directly with a UNC path. We can spin up an SMB server using npackets smbserver.py which allows anonymous authentication by default as follows: inpacket-smb server -smb2 support share and password. Now we can include our script by using a UNC path. So //rp/share/shell.php and specify the command with and cmd equals who am I, as we did earlier. As we can see, this attack works in including our remote script, and we do not need any non-default settings to be enabled. However, we must note that this technique is more likely to work if we were on the same network, as accessing remote SMB servers over the internet may be disabled by default, depending on the Windows server configurations. So, our question down below: attack the target, gain command execution by exploiting the RFI vulnerability, and then look for the flag under one of these directories in the root directory. So we're spawning our target. We'll grab our pwn box. There we go. And grab the target IP, and we'll visit the target in our browser. Unable to connect. Let's take a look. Boom, boom, boom. Existing pwn box instances will automatically switch to the new VPN server. So let's download connection in my workstation. So let's try it again here. It's not working. How about just our browser, if anything? And then if that doesn't work, we'll just have to launch it from here. Academy VPN, most likely. Okay, so we'll just start this instance and use that. So the first thing we'll take a look at is this. We'll see if we can just load the page within the page, and then we'll try hosting this shell with Python. There we go. So let's try visiting the page. There we go, loads this time. And we're gonna try just loading this. See if it's vulnerable. So English, clear this out and paste. And so that works. So our history is within our history. And then we'll open our command line. We'll run this command to spawn a shell code in a file. And then we'll do python 3-m http.server port 80 to host. Okay, permission denied. Let's see. Let's see if we can do it on port 8000. And then grab our IP. And see if we can load that here. /shell.php, and it was the ampersand cmd equals. Let's try ID. Thinking. Oh yes, we forgot the port number, 8000. Try it again. It's requesting it. It got the GET request. And here we go. ID this. So we have the working shell, and now it's asking for the flag and the root directory. So we're going to list now in our root directory. So list +sign root directory. And not seeing anything, so we'll check in root. And that didn't load. Let's try it one more time. Make sure 8000 is there. Cell CMD. Under one of the directories in this. So it's within one of these. Oh, most likely this one, exercise. Okay. And then flag.txt. So we'll cat that. For the flag. So we tested to see if the 127.0.0.1 would work. That worked, so then we hosted the shell.php to then, in this instance, I did port 8000. We ran the commands to make sure we could maneuver in the system, and then we found our flag by an educated guess. Carrying on with LFI and file uploads. File upload functionalities are ubiquitous in most modern web applications, as users usually need to configure their profile and usage of the web application by uploading their data. For attackers, the ability to store files on the backend server may extend the exploitation of many vulnerabilities, like a file inclusion vulnerability. The file upload attacks module covers different techniques on how to exploit file upload forms and functionalities. However, for the attack we are going to discuss in this section, we do not require the file upload form to be vulnerable, but merely allow us to upload files. If the vulnerable function has code execute capabilities, then the code within the file we upload will get executed if we include it, regardless of the file extension or file type. For example, we can upload an image file, for example, image.jpg, and store a PHP web shell code within it instead of image data. And if we include it through the LFI vulnerability, the PHP code will get executed and we will have remote code execution. As mentioned before in the first section, the following are the functions that allow executing code with file inclusion, any of which would work with this section's attacks. So image upload. Image upload is very common in most modern web applications, as uploading images is widely regarded as safe if the upload function is securely coded. However, as discussed earlier, the vulnerability in this case is not in the file upload form, but the file inclusion functionality. Crafting malicious image. Our first step is to create a malicious image containing a PHP web shell code that still looks and works as an image. So we will use an allowed image extension in our file name, for example shell.gif, and should also include the image magic bytes at the beginning of the file content, for example gif8, just in case the upload form checks for both the extension and content type as well. We can do so as follows. This file on its own is completely harmless and would not affect normal web applications in the slightest. However, if we combine it with an LFI vulnerability, then we may be able to reach remote code execution. Note: we are using a GIF image in this case since its magic bytes are easily typed, as they are ASCII characters, while other extensions have magic bytes in binary that we would need to URL encode. However, this attack would work with any allowed image or file type. The file upload attacks module goes more in depth for file type attacks, and the same logic can be applied here. Now we need to upload our malicious image file. To do so, we can go to the Profile Settings page and click on the avatar image to select our image, and then click on Upload, and our image should get successfully uploaded. Uploaded file path. Once we've uploaded our file, all we need to do is include it through the LFI vulnerability. To include the uploaded file, we need to know the path to our uploaded file. In most cases, especially with images, we would get access to our uploaded file and can get its path from its URL. In our case, if we inspect the source code after uploading the image, we can get its URL. Note: as we can see, we can use /profile_images /shell.gif for the file path. If we do not know where the file is uploaded, then we can fuzz for an uploads directory and then fuzz for our uploaded file, though this may not always work, as some web applications properly hide the uploaded files. With the uploaded file path at hand, all we need to do is to include the uploaded file in the LFI vulnerable function, and the PHP code should get executed as follows. As we can see, we included our file and successfully executed the id command. Note: to include to our uploaded file, we used /profile_images, as in this case the LFI vulnerability does not prefix any directories before our input. In case it did prefix a directory before our input, then we simply need to // out of that directory, and then use our URL path as we learned in previous sections. Zip upload. As mentioned earlier, the above technique is very reliable and should work in most cases, and with most web frameworks, as long as the vulnerable function allows code execution. There are a couple of other PHP-only techniques that utilize PHP wrappers to achieve the same goal. These techniques may become handy in some specific cases where the above technique does not work. We can utilize the zip wrapper to execute PHP code. However, this wrapper isn't enabled by default, so this method may not always work. To do so, we can start by crafting a PHP web shell script and zipping it into a zip archive named shell.jpg as follows. Note: even though we named our zip archive as shell.jpg, some upload forms may still detect our file as a zip archive through content type tests and disallow its upload. So this attack has a higher chance of working if the upload of zip archives is allowed. So once we upload the shell.jpg archive, we can include it with the zip wrapper as zip ://shell.jpg, and then refer to any files within it with pound or hashtag shell.php URL encoded. Finally, we can execute commands as we always do with and &cmd equals ID as follows. So that pound is URL encoded. As we can see, this method also works in executing commands through zipped PHP scripts. Note: we added the uploads directory /profile_images before the file name, as the vulnerable page index.php is the main directory. Far upload. Finally, we can use the far wrapper to achieve a similar result. To do so, we will first write the following PHP script into a shell.php file. This script can be compiled into a far file that, when called, would write a web shell to a shell.txt subfile, which we can interact with. We can compile it into a far file and rename it to shell.jpg as follows. And now we should have a far file called shell.jpg. Once we upload it to the web application, we can simply call it with the far wrapper and provide its URL path, and then specify the far subfile with /shell.txt URL encoded to get the output of the command we specify with &cmd equals ID. So, like before, that / is what's URL encoded there. And as we can see, the ID command was successfully executed. Both the zip and far wrapper methods should be considered as alternatives in case the first method did not work, as the first method we discussed is the most reliable among the three. Note: there's another and obsolete LFI/uploads attack worth noting, which occurs if file uploads is enabled in the PHP configurations and the PHP info page is somehow exposed to us. However, this attack is not very common, as it has very specific requirements for it to work. LFI plus uploads enabled plus old PHP plus exposed PHP info. If you're interested in knowing more about it, you can refer to this link. And we've got another question below. Use any of the techniques covered in this section to gain RCE and read the flag. So we'll do the same thing as before. We'll load it up in the browser, and we'll go ahead and use the first method here. So we'll first need to craft the exploit, shell.gif, in our command line. So profile settings. I think that's where the upload is. And we'll kill this, and clear this. So we're running the command to create the shell in our photo. And we're going to upload file not allowed. So let's see what I didn't specify anything, so let's see why it says that. Update your image. Okay. So it's on our home, shell.gif, and upload. Okay, so that worked. That was successfully uploaded. Now we'll take a look at our second step. We need to find where it is. So we can look at the source code of the photo. So under profile settings, and then we right click and view page source. So we are looking for, here we go. So this is our directory. So we'll copy that, and we might be able to click on that. Okay, so this is our full URL, and then it's asking to copy this and paste this into our parameter, in our vulnerable parameter. Which is our language. We're going to add the and CMD after that. So we have the full URL to our image, and then ending it with and CMD equals, let's go with list. And that didn't work. Let's take a look here. Profile images. Oh, maybe we don't need the full, or maybe we need the dot. Yes, we need the dot. I have the full IP import here, so let's just clear that out. Okay. Okay, so it's able to list what's in our uploads and our profile underscore images directory. So then let's see what's in our root directory. List what's there. List +, backslash. And there's our flag. We'll go ahead and copy this. And then we're going to cat it. So just cat +, paste. Oh, don't forget the backslash before the image file, or the flag. Okay, so we'll try it again. Enter. Saying GIF 8, let's see. Backslash GIF. Well, let's try that. And I don't think that's it. So we're catting. So let's try this. Oops. So let's back it up. Take a step back. List plus backslash. Perhaps this is all we need. We'll try that. Try plus sign. GIF 8. Maybe the dot. Same thing. We'll just try to paste that here. Let's see. No, it wants us to read it. So profile, images, shell.gif, command. We're trying to cat this. It's asking for GIF. GIF 8. So we're catting the root. And now that's not working. Oh wait, list. My bad. Okay. So this looks like it. We'll try it one more time. Copy. Oh geez. Freaking out here. So I wonder if this would work. Instead of loading it through the command, what if we tried loading it just through here? I'll have to go back to, right? Profile. Let's just see if this will work. Are you using the correct upload directory? Correct upload directory. Yes, we are. And we're trying to, let's just try to list it, perhaps. See if that works. and it just says GIF 8. But when we try to cat it, it doesn't want to read it. So what about listing? Oh, was that what I was doing? Cat plus? Same thing. Cat plus GIF 8. There we go. Okay, so it didn't want the GIF 8. It wanted cat plus backslash and this string .txt. So GIF 8. So for some reason it's adding this, but we're getting hack the box, upload, LFI, execute equals RCE. And there we go. Log poisoning. We have seen in previous sections that if we include any file that contains PHP code, it will get executed, as long as the vulnerable function has the execute privileges. The attacks we will discuss in this section all rely on the same concept, writing PHP code in a field we control that gets logged into a log file. For example, poison/contaminate the log file, and then include that log file to execute the PHP code. For this attack to work, the PHP web application should have read privileges over the logged files, which vary from one server to another. As was the case in the previous section, any of the following functions with execute privileges should be vulnerable to these attacks. PHP session poisoning. Most PHP web applications utilize PHP session ID cookies, which can hold specific user-related data on the back end, so the web application can keep track of the user details through their cookies. These details are stored in session files on the back end and saved in var lib PHP sessions on Linux and in Windows temp on Windows. The name of the file that contains our user's data matches the name of our PHP session ID cookie with the ses underscore prefix. For example, if the PHP session ID cookie is set to that string, then its located on the disk. Then its location on the disk would be var lib PHP sessions ses underscore that string. So the first thing we need to do in a PHP session poisoning attack is to examine our PHP ses ID session file and see if it contains any data we can control and poison. So let's first check if we have a PHP session ID cookie set in our session. As we can see, our PHP sesh ID cookie value is as follows, so it should be stored at var lib PHP sessions ses underscore that string. Let's try to include this session file through the LFI vulnerability and view its contents. Note: as you may easily guess, the cookie value will differ from one session to another, so you need to use the cookie value you find in your own session to perform the same attack. We can see that the session file contains two values: page, which shows the selected language is page, and preference, which shows the selected language. The preference value is not under our control, as we did not specify it anywhere and must be automatically specified. However, the page value is under our control, as we can control it through the language parameter. Let's try setting the value of page, a custom value, for example language parameter, and see if it changes in the session file. We can do so by simply visiting the page with $language equals session underscore poisoning, specified as follows. So now let's include the session file once again to look at its contents. This time the session file contains session underscore poisoning instead of es.php, which confirms our ability to control the value of page in the sessions file. Our next step is to perform the poisoning step by writing PHP code to the session file. We can write a basic PHP web shell by changing the language parameter to a URL encoded web shell as follows. Finally, we can include the session file and use the and cmd equals id to execute a command. To execute another command, the session file has to be poisoned with the web shell again, as it gets overwritten with that after our last inclusion. Ideally, we would use the poisoned web shell to write a permanent web shell to the web directory or send a reverse shell for easier interaction. Server log poisoning. Both Apache and Nginx maintain various log files, such as access.log or error.log. The access.log file contains various information about all requests made to the server, including each request's user agent header. As we can control the user agent header in our requests, we can use it to poison the server logs as we did above. Once poisoned, we need to include the logs through the LFI vulnerability, and for that we need to have read access over the logs. Nginx logs are readable by low privilege users by default, for example -data, while the Apache logs are only readable by users with high privileges, for example root or admin groups. However, in older or misconfigured Apache servers, these logs may be readable by low privileged users. By default, Apache logs are located in var log apache 2 on Linux and nc examp apache logs on Windows, while Nginx logs are located in var log nginx on Linux and nc nginx log on Windows. However, the logs may be in a different location in some cases, so we may use an LFI word list to fuzz for their locations, as will be discussed in the next section. So let's try including the Apache access log from the var log apache to access.log and see what we get. As we can see, we can read the log. The log contains the remote IP address, request page, response code, and user agent header. As mentioned earlier, the user agent header is controlled by us through the HTTP request headers, so we should be able to poison this value. Tip: logs tend to be huge, and loading them in an LFI vulnerability may take a load to while, or even crash the server in the worst case scenarios. So be careful and efficient with them in a production environment, and don't send unnecessary requests. To do so, we will use Burp Suite to intercept our earlier LFI request and modify the user agent header to Apache log poisoning. Note, as all requests to the server get logged, we can poison any request to the web application and not necessarily the LFI one as we did above. As expected, our custom user agent value is visible in the included log file. Now we can poison the user agent header by setting it to a basic PHP web shell. We may also poison the log by sending a request through curl as follows. As the log should now contain PHP code, the LFI vulnerability should execute this code, and we should be able to gain remote code execution. We can specify a command to be executed with $cmd equals ID. We see that we successfully executed the command. The exact same attack can be carried out on Nginx logs as well. Tip: the user agent header is also shown on process files under the Linux proc directory process. So we can try including the proc self environ or proc self fd / N, where N is a PID usually set between 0 and 50, and we may be able to perform the same attack on these files. This may become handy in case we did not have read access over the server logs. However, these files may only be readable by privileged users as well. Finally, there are other similar log poisoning techniques that we may utilize on various system logs, depending on which logs we have read access over. The following are some of the service logs we may be able to read: varlog sshd.log, varlog mail, and varlog vs ftpd.log. We should first attempt reading these logs through LFI, and if we do not have access to them, we can try to poison them as we did above. For example, if the SSH or FTP services are exposed to us and we can read their logs through LFI, then we can try logging into them and set the user name to PHP code, and upon including their logs, the PHP code would execute. The same applies with the mail services, as we can send an email containing PHP code, and upon its log inclusion, the PHP code would execute. We can generalize this technique to any logs that log a parameter we control and that we can read through the LFI vulnerability. So we'll spawn our target and look at this next question. Use any of the techniques covered in this section to gain RCE. Then submit the output of the following command. So print working directory pwd. So we'll use just the curl. It's simple enough. We'll copy this into our command line and change out our server IP with our port number as well, and hit enter. Okay, so that should have gone through, and then we will try to load it. So let's see where they load it after they curl it. So in the language parameter, they're going var log apache2 access.log. So it should also work in curl. So let's try that. So let's do the same thing. We'll clear out our header and try that index.php (language) equals, and then var log apache2 access.log. So, there's two questions. Var log apache2 access.log, and then ampersand cmd equals pwd. So ampersand cmd equals pwd. and see if that worked here. var log apache2 access.log, var log apache2 access.log, and cmd equals. So, okay, so we would have to do it through our burp because it wouldn't output the access log here. Just to verify, let's minimize this. Well, isn't this it here? Let's try just ID. So it's getting our last request, so it's our printing work directory. So let's just start up burp and take a look at this one more time. We can also try in our browser. So let's try that. We'll just start this up just in case and visit this in the browser. var language. Okay, so it's showing here, but it's not showing the output, right? Because we didn't, because the first curl did not work. So let's try it again. And then see if this loads. Okay, it's kind of messy. Let's view the page source here. Okay. Scroll down. So we tried to send it through curl, but that didn't work. I think that's why it's not working there. So let's do it through language equals that. Maybe because this was wrong, we need to send it to the log. So let's try that. Let's see. So our original command was this, so let's try if we can do language equals var log apache2 /access.log. So now this should send as so, or like so, our user agent with a PHP shell to the access log. We were sending it just to index.php previously. So we'll try to print now and see what happens. Access log, print working directory. Try it in the browser as well. So this one is our server log poisoning. We'll try it with burp and then see what happens here. Okay, so we'll start our proxy. We've got burp up. Let's start it here. It's on. And we'll hit enter. And see if it comes through after we send it to repeater. It's kind of tight in here, but this is what it should look like. var log apache2 access.log and command equals print working directory. And command equals print working directory. And then at the bottom it should render. So let's send it through and check our response in our log here. Print working directory. It doesn't show here. So let's try doing the shell again in our user agent first. So we'll clear this out and grab our shell. Don't forget that first caret. So we're pasting it in the user agent, pasting it there. It's in our language var log apache2 access.log. That looks good. We'll hit send. Check the response. See if it is there. So it should be here, but I didn't see it. It was the last minute there. Yeah, that was the last thing that went through the print working directory. So then we'll try it again. And cmd equals print working directory. Let's just clear out the user agent this time. And send it. And see what we get here. So this is 2240. 2240. Okay. This is our working directory. var HTML. Remember previously it said something about persistence. Basically it's like you have to send it into the log. The next time you send it through has to be a command. But then to do another command, you'd have to set it up again. So we'll paste that into our answer. And then try to use a different technique to gain RCE and read the flag at that. So this was through burp. It's asking us to try it through a different one. Let's try it here again. Access log. And then this time we just want to command =, list what's in our root directory. So let's just try curl and see. So 42. And that didn't populate. Let's keep that -s. So I'm not getting anything here. Curl. Okay. So it's asking us to try a different route. So we tried the server log poisoning. Let's go back to one of these here. So we have PHP session poisoning. So let's try this route. So the PHP session is stored here, varlib PHP sessions sesh underscore our cookie. So let's bring it up into our browser. So language, English. We need to turn this off, our burp. Try it again here, language, English. Okay. We'll just copy this first, slash varlib PHP session. So we're going to paste that here and then grab our PHP ID. Or we'll try this first. This is our URL encoded PHP shell. So let's just try. Into the language parameter, paste. Okay, and then we'll try to grab our PHP session, our cookie here. I think that's memory, right? Or storage. Okay, cookies, PHP session. So we're going to copy our value. In a moment, we're going to copy the directory, which was this, and then paste in our cookie. So paste, and then copy our value here. See what pastes. We don't need the quotes. We don't need PHP session ID. And then we need the and command, correct? And cmd equals ID. So it's asking for read the flag. So let us list what's in the root directory first. And cmd equals list +sign \. We can close this out and see if this actually loads here. Okay, this is our flag. Let's see if we can cat it. Oops. It really wants to open that right now. So cat that, and then, or copy that, and then we're going to cat that. Select language. So we might need to do what we did before. So let's just copy this. This is the command we need. We're catting the flag, but we need to go back to the shell URL to make sure it's uploaded. Okay, and then paste in our updated one. Okay, there we go. So just like before, it's a one-hit wonder. You gotta send it through, run the command, send through the shell again, run the command, one at a time. Kind of annoying, but let's grab this flag again. Did not copy. Let's view the page source just in case it's cut off. Okay, there we go. And good to go. Carrying on. Automated scanning. It It is essential to understand how file inclusion attacks work and how we can manually craft advanced payloads and use custom techniques to reach remote code execution. This is because in many cases, for us to exploit the vulnerability, it may require a custom payload that matches its specific configurations. Furthermore, when dealing with security measures like a WAF or a firewall, we have to apply our understanding to see how a specific payload or character is being blocked and attempt to craft a custom payload to work around it. We may not need to manually exploit the LFI vulnerability in many trivial cases. There are many automated methods that can help us quickly identify and exploit trivial LFI vulnerabilities. We can utilize fuzzing tools to test a huge list of common LFI payloads and see if any of them work. Or we can utilize specialized LFI tools to test for such vulnerabilities. This is what we'll discuss in this section. Fuzzing parameters. The HTML forms users can use on web applications front end tend to be properly tested and well secured against different web attacks. However, in many cases, the page may have other exposed parameters that are not linked to any HTML forms, and hence normal users would never access or unintentionally cause harm through. This is why it may be important to fuzz for exposed parameters, as they tend not to be as secure as public ones. The Attacking Web Applications with FUF module goes into details on how we can fuzz for get or post parameters. For example, we can fuzz the page for common get parameters as follows. Once we identify an exposed parameter that isn't linked to any forms we tested, we can perform all of the LFI tests discussed in this module. This is not unique to LFI vulnerabilities, but also applies to most web vulnerabilities discussed in other modules, as exposed parameters may be vulnerable to any other vulnerability as well. Tip: for a more precise scan, we can limit our scan to the most popular LFI parameters found on this link. LFI word lists. So far in this module, we have been manually crafting our LFI payloads to test for LFI vulnerabilities. This is because manual testing is more reliable and can find LFI vulnerabilities that may not have been identified otherwise, as discussed earlier. However, in many cases, we may want to run a quick test on a parameter to see if it is vulnerable to any common LFI payload, which may save us time in web applications where we need to test for various vulnerabilities. There are a number of LFI word lists we can use for this scan. A good word list is LFI-jhaddix.txt, as it contains various bypasses and common files, so it makes it easy to run several tests at once. We can use this word list to fuzz the language parameter we have been testing throughout the module as follows. As we can see, the scan yielded a number of LFI payloads that can be used to exploit the vulnerability. Once we have the identified payloads, we should manually test them to verify that they work as expected and show the included file content. Fuzzing server files. In addition to fuzzing LFI payloads, there are different server files that may be helpful in our LFI exploitation, so it would be helpful to know where such files exist and whether we can read them. Such files include server web root path, server configurations file, and server logs. Server web root. We may need to know the full server web root path to complete our exploitation in some cases. For example, if we wanted to locate a file we uploaded, but we cannot reach its uploads directory through relative paths, for example, //uploads, in such cases, we may need to figure out the server web root path, so then we can locate our uploaded files through absolute paths instead of relative paths. To do so, we can fuzz for the index.php file through common web root paths, which we can find in this word list for Linux or this word list for Windows. Depending on our LFI situation, we may need to add a few back directories and then add our index.php afterwards. Following is an example of how we can do all of this with FUF. As we can see, the scan indeed did identify the correct web root path at var HTML or var www.html. We may also use the LFI, that same word list from before, as it also contains various payloads that may reveal the web root. If this does not help us in identifying the web root, then our best choice would be to read the server configurations, as they tend to contain the web root and other important information, as we'll see next. Server logs and configurations. As we have seen in the previous section, we may need to be able to identify the correct logs directory to be able to perform the log poisoning attacks we discussed. Furthermore, as we discussed, we may also need to read the server configurations to be able to identify the server web root path and other important information, like the logs path. To do so, we can use the same word list, as it contains many of the server logs and configurations paths we may be interested in. If we wanted a more precise scan, we can use this word list for Linux and this word list for Windows, though they are not part of sec lists, so we need to download them first. Let's try the Linux word list against our LFI vulnerability and see what we get. As we can see, the scan returned over 60 results, many of which were not identified with the jHadX word list, which shows us that a precise scan is more important in certain cases. Now we can try reading any of these files to see whether we can get their content. We'll read etc apache2 apache2.conf, as it is a known path for the Apache server configuration. As we can see, we do get the default web root path and the log path. However, in this case, the log path is using a global Apache variable, Apache log dir, which are found in another file we saw above, which is etc password invars. And we can read it to find the variable values. As we can see, the Apache log dir variable is set to var log apache2. And the previous configurations told us that the log files are at access.log and error.log, which we have discussed in the previous section. Pardon me. Of course, we can simply use a word list to find the logs, as multiple word lists we used in this section did show the log location. But this exercise shows us how we can manually go through identified files and then use the information we find to further identify more files and important information. This is quite similar to when we read different file sources in the PHP filter section, and such efforts may reveal previously unknown information about the web application, which we can use further to exploit it. LFI tools. Finally, we can utilize a number of LFI tools to automate much of this process we have been learning, which may save some time in some cases, but may also miss many vulnerabilities and files we may otherwise identify through manual testing. The most common LFI tools are LFI Suite, LFI Freak, and LFI. We can also search GitHub for various other LFI tools and scripts. But in general, most tools perform the same tasks with varying levels of success and accuracy. Unfortunately, most of these tools are not maintained and rely on the outdated Python 2, so using them may not be a long-term solution. Try downloading any of the above tools and test them on any of the exercises we've used in this module to see their level of accuracy. And we've got a question here. Fuzz the web application for exposed parameters, then try to exploit it with one of the LFI word lists to read \flag.text. So let's take a look. So try to fuzz for exposed parameters first. We'll use the, let's see, exposed parameters here. Burp parameter names. So we'll use this first. We'll clear this and paste this in. And our IP and port. So we're fuffing with our parameter word list and pasting this in. There we go. Fuzz equals value. So we're going to get everything back, but remember we have to cut out everything that returns with a 2309 for good parameters. So we have a view. That might be it. And view is correct. So then it says try to exploit it with one of the LFI word lists to read \flag.txt. So we'll want to do the same thing. Let's see if we have it. LFI word list, LFI fuzz. Okay. So LFI Linux. Yeah, we'll try that one, I guess. Oh, I guess I have to download it first. Let's see if the Hadix one works. Here we go. So we've got that. So we're LFI fuzzing. Our parameter is view. And our correct. So view is here. And then our IP and port. So copying this again, pasting that in, and running it. Looks good, except for the return, we don't want 2000, we want 5, or we do want 1935. So we've got all these dots, a million dots. So let's copy that and see if we can curl. That. Copy, paste, clear out fuzz, and see if we can read Etsy password. Okay, we can read Etsy password. So then we want to read \flag. So clear out Etsy password. Just flag. Was it .txt? And there we go. Automation finds hidden gems. Automation finds hidden gems. That was a lot faster than everything else. Cool stuff. Carrying on. File inclusion prevention. This module has discussed various ways to detect and exploit file inclusion vulnerabilities, along with different security bypasses and remote code execution techniques we can utilize. With that understanding of how to identify file inclusion vulnerabilities through penetration testing, we should now learn how to patch these vulnerabilities and harden our systems to reduce the chances of their occurrence and reduce the impact if they do. File inclusion prevention. The most effective thing we can do to reduce file inclusion vulnerabilities is to avoid passing any user-controlled inputs into any file inclusion functions or APIs. The page should be able to dynamically load assets on the back end with no user interaction whatsoever. Furthermore, in the first section of this module, we discussed different functions that may be utilized to include other files within a page and mentioned the privileges each function has. Whenever any of these functions is used, we should ensure that no user input is directly going into them. Of course, this list of functions is not comprehensive, so we should generally consider any function that can read files. In some cases, this may not be feasible, as it may require changing the whole architecture of an existing web application. In such cases, we should utilize a limited whitelist of allowed user inputs and match each input to the file to be loaded while having a default value for all other inputs. If we are dealing with an existing web application, we can create a whitelist that contains all existing paths used in the front end, and then utilize this list to match the user input. Such a whitelist can have many shapes, like a database table that matches IDs to files, a case match script that matches names to files, or even a static JSON map with names and files that can be matched. Once this is implemented, the user input is not going into the function, but the matched files are used in the function, which avoids file inclusion vulnerabilities. Preventing directory traversal. If attackers can control the directory, they can escape the web application and attack something they are more familiar with, or use a universal attack chain. As we have discussed throughout the module, directory traversal could potentially allow attackers to do any of the following: read ETSI password and potentially find SSH keys or no valid usernames for a password spray attack, find other services on the box such as Tomcat and read the tomcat-users.xml file, discover valid PHP session cookies and perform session hijacking, and read current web application configuration and source code. The best way to prevent directory traversal is to use your programming languages or frameworks built-in tool to pull only the file name. For example, PHP has base name, which will read the path and only return the file name portion. If only a file name is given, then it will return just the file name. If just the path is given, it will treat whatever is after the final / as the file name. The downside to this method is that if the application needs to enter any directories, it will not be able to do it. If you create your own functions to do this method, it is possible you are not accounting for a weird edge case. For example, if in your bash terminal, go to your home directory cd / and run the command as follows: cat // ETSI password. You'll see bash allows for the question mark and wildcards to be used as a ... Now php-a to enter the PHP command line interpreter and run echo fileget contents as that string. You'll see PHP does not have the same behavior with the wildcards. If you replace question mark and asterisk with ... the command will work as expected. This demonstrates that there is an edge case with our above function. If we have PHP execute bash with the system function, the attacker would be able to bypass our directory traversal prevention. If we use native functions to the framework we are in, there's a chance other users would catch edge cases like this and fix it before it gets exploited in our web application. Furthermore, we can sanitize the user input. to recursively remove any attempts of traversing directories as follows. As we can see, this code recursively removes ... substrings. So even if the resulting string contains ... it would still remove it, which would prevent some of the bypasses we attempted in this module. Web server configuration. Several configurations may also be utilized to reduce the impact of file inclusion vulnerabilities in case they occur. For example, we should globally disable the inclusion of remote files. In PHP, this can be done by setting allow URL fopen and allow URL include to off. It's also often possible to lock web applications to their web root directory, preventing them from accessing non-web related files. The most common way to do this in today's age is by running the application within Docker. However, if that's not an option, many languages often have a way to prevent accessing files outside of the web directory. In PHP, that can be done by adding open_base directory equals var www and the PHP any file. Furthermore, you should ensure that certain potential dangerous modules are disabled, like PHP expect mod_user_dir. If these configurations are applied to prevent it should prevent accessing files outside the web application folder. So even if an LFI vulnerability is identified, its impact would be reduced. Web Application Firewall, WAF. The universal way to harden web applications is to utilize a web application firewall, such as mod security. When dealing with web application firewalls, the most important thing to avoid is false positives and blocking non-malicious requests. Mod security minimizes false positives by offering a permissive mode, which will only report things it would have blocked. This lets defenders tune the rules to make sure no legitimate request is blocked. Even if the organization never wants to return the WAF to blocking mode, just having it in permissive mode can be an early warning sign that your application is being attacked. Pardon me. Finally, it is important to remember that the purpose of hardening is to give the application a stronger exterior shell. So when an attack does happen, the defenders have time to defend. According to the FireEye Trends report of 2020, the average time it took a company to detect hackers was 30 days. With proper hardening, attackers will leave many more signs, and the organization will hopefully detect these events even quicker. It is important to understand the goal of hardening is not to make your system unhackable, meaning you cannot neglect watching logs over a hardened system because it is secure. Hardened systems should be continually tested, especially after 0 day is released for a related application to your system. For example, Apache Struts, Rails, Django, etc. In most cases, the 0 day would work, but thanks to hardening, it may generate unique logs, which made it possible to confirm whether the exploit was used against the system or not. Alright, so we should spawn the target and answer a couple questions. What is the full path to the php.ini file for Apache? And number 2, edit the php.ini file to block system. Then try to execute PHP code that uses system. Read the var log apache2 error log file and fill in the blank. System has been disabled for, I'm just going to guess, security. That just makes sense. What is the full path to php.ini file? So the php.ini file, I think that was up here, right? full path to PHP any file. PHP any file. Let's search it. PHP any file. Let's do any. Var double double double. Is that our answer? Var double 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 PHP dot any. No. Okay. And for Apache. Okay, let's just SSH into this like it says. SSH as HTB-student at our IP address and our password. Copy that. Oops. I'll just copy that. Good to go. Yes. So HTB underscore, right? At, and then paste. And that didn't work. Let's try to copy and paste it. Nope, doesn't want it. Okay. I'm just gonna paste it here. Okay. There we go. Paste that in, enter. Okay, list. So list.la. So let's try to find the PHP any file. I think that's just what it's asking here. So var list double 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 list cd HTML list find php.any find dot cd and the same thing. We can also probably just Google it. So it's asking, what is the full path? Full path of PHP any. And Apache. Ooh, it might be asking specifically for the example there, or to check where Apache has our PHP any file. Let's try this command. php-r php info. Okay, there we go. So it wanted us to find it. Here it is in our system here. Incorrect. Okay. Configuration file path. What is the full path to the PHP file for Apache? Let's try this one and see. Maybe we don't want to be in SSH. I mean, that's what it's saying. etc php 7.4 client php any. Maybe don't include the php any. Incorrect. Maybe not. Hint? No hint. Cheat sheet. Any. I don't think it's on here. PHP. Let's see if we can open this and see if it's on here. find php dot any. Okay, here we go. Apache php any. That's what it was asking. So let's see if that works. For Apache php any has a /. Let's try back. Or let's try that. As it was. Incorrect. / incorrect. Let's see. Let's jump back. There are 39 of these, so then let us see. Depends on our version too. Etsy PHP Apache 2. Etsy PHP. Okay, let's search. List cd Etsy list cd Apache 2 list and list blah. So where is our PHP file for PHP any file for Apache? Maybe it's here. Var log. We can check. php.any Apache 2 php.any. These are our logs. Show. What did it say from our find? It kind of looked everywhere. Okay, I don't know if that will help us. This is what we tried before. Try it again. And it's saying it's there. So what if we just go to, let's see, PHP 7.4 list cd Apache 2. That's different. List. There we go. So this might be it. Etsy PHP 7.4 Apache 2 php.any. Etsy PHP 7.4. We need a version number in there. Apache 2 php.any. Okay. There we go. And mark as complete. We'll go ahead and pause here for today, and we'll continue this in part 4. Once again, my name is Sleeper, and that's a wrap. Until next time.